Chapter 5, Part 1, Defining Terms Used in Organic Reactions and Carbocation Rearrangements. First up, I'm going to present a chapter summary just to help us understand what's coming up. So this is Part 1. Part 2 is an introduction to electrophilic addition reactions. Part 3 is hydrohalogenation and Markovnikov addition. Part 4, hydration of alkenes. Part 5, halogenation and hydrogenation of alkenes. Part 6, reactions of alkynes and drawing alkynes and their products. And Part 7, how to make helpful reaction flashcards. First up, for our definitions, we have electrophiles. Electrophile means electron-seeking or electron-loving. Electrophiles are electron poor, meaning they are lacking in electrons, so they are not capable of initiating a reaction. Electrophiles essentially wait around to be attacked by something that actually does have electrons. Remember, electrons do the chemistry, and that's why we say that curved arrows show the flow of electrons. Electrophiles have a positive charge or a partial positive charge. Electrophiles are Lewis acids, meaning they are electron acceptors. A proton is a common electrophile. You will see that a lot kicking off some of the reactions in this chapter. And I often use capital E with the plus sign as a shorthand for the word electrophile. Our next word is nucleophile. Nucleophile means nucleus seeking or nucleus loving. This means that nucleophiles want to make a covalent bond. They want to use their electrons to make a bond with another atom. Nucleophiles are electron dense, meaning they are electron rich, and they are the initiators in their reactions. They have a negative charge as an actual formal charge, or they may have a partial negative charge as a result of being a polar molecule or having a polar bond. The electron density can come from lone pairs of electrons or pi bonds. Nucleophiles are typically weak Lewis bases. That makes them electron donors. I put typically weak in parentheses here because you can have strong bases that we use as nucleophiles, and you will see examples of that later on in this course. But typically when we're looking for a nucleophile, and especially when we start defining good versus bad nucleophiles, we're often looking for weaker bases because molecules that are strong bases tend to act as just that, bases. Some common nucleophiles are cyanide, which has a negative charge on the carbon, halide ions, which you'll see a lot in this chapter, water, which you will also see, alkoxides, which are the conjugate bases of alcohols, and ammonia and amines. And these are not the only nucleophiles. These are just the ones you're going to see most commonly and coming up soon in the course. As we go throughout the course, you'll learn many new nucleophiles. I often use nuke with a negative sign as my usual shorthand for nucleophile. Carbocations are sp2 hybridized carbon atoms that only have 3 bonds and therefore a positive charge. Since they are sp2 hybridized, it's important to point out that they are also trigonal planar. They are going to be flat. Carbocations can be classified by the number of carbons attached to the positively charged carbon. So, for example, in this little chart here, we have this carbocation, which is called a methyl carbocation. We will use Me as shorthand here. In this example of a carbocation, the positively charged carbon is only attached to one other carbon. That makes this a primary carbocation, and I've drawn the structures below in line bond format as well where possible. You can't really do that for a methyl carbocation. This next one, the carbocation carbon, is attached to 2 carbons. That makes this a secondary carbocation. The next one is attached to 3 carbon atoms, so this is a tertiary carbocation. The more substituted a carbocation is, the more stable it is. This is due to an effect called hyperconjugation, where the nearby electron clouds of alkyl groups help to stabilize the carbocation. So the order of stability for carbocations is tertiary is more stable, it's going to be lower energy, they're also going to form more easily, and then secondary, primary, and then methyl. You will not usually see methyl carbocations because they don't have any alkyl groups to stabilize them. The carbocations you will see most commonly will be tertiary and secondary. Now, because carbocations have this relative stability that we just discussed, it's common for carbocations to undergo what we call a rearrangement. So primary and secondary carbocations can undergo a rearrangement in order to form a more stable carbocation. The most common rearrangement that you'll see is a secondary carbocation rearranging to tertiary. There are two types of rearrangements. The first one is called a hydride shift. This is called a hydride shift because we are moving a hydrogen and also 2 electrons, which gives it a negative charge. This is a hydrogen atom on a more substituted carbon, and the 2 electrons in its covalent bond are going to shift to the neighboring carbocation carbon atom. The other type of rearrangement is called an alkyl shift. There are actually several different types of alkyl shifts. The one that we will see the most in this course is a methyl shift. This is when a small carbon substituent, or you can also see a ring and a ring expansion, but that's not really something we're going to cover in this course, shifts to the neighboring less substituted carbocation carbon atom. Rearrangements occur only if the resulting carbocation would be more stable. You will never see something like a secondary carbocation rearranges to a secondary carbocation because that would not be an improvement, and the actual act of rearrangement has a significant energy cost. So there also has to be a significant energy payoff. So you'll see things like secondary going to tertiary. Sometimes you'll see primary going to secondary. It's just primary carbocations don't form as easily, and so you don't see them very often. And then one thing you will absolutely not see is taking something like a secondary carbocation and turning it into a primary. We are never going to take anything down in stability. So let's look at how those rearrangements actually work. So in this example, we are doing explicitly a hydride shift. And the typical setup for a hydride shift is that you have a secondary carbocation next to a tertiary carbon. And the reason that this happens the way it does is that this tertiary carbon has a hydrogen atom on it. And we are going to take this hydrogen atom along with the 2 electrons in the covalent bond, and we are going to essentially slide it over to this carbon. So this hydrogen and the bond that's on are just sliding over to the neighboring carbocation carbon. And what this does for us is to relocate the carbocation to the more substituted carbon. Now, the way that we did that is we took this hydrogen and its 2 electrons and put it on the carbocation carbon. So now the carbocation carbon is neutral, and the carbon that we stole those electrons from becomes positive. Sometimes students really struggle with carbocation rearrangements because it seems like you're taking the positive charge and moving it here. But a positive charge is an indicator of a lack of something. And if you don't have something, you can't move it, if that makes sense. If you were to walk into a room that was too bright, you couldn't say, let's add more dark to this. The only way that you could make a room less bright would be to remove some light. So electrons are kind of like that. The only way you can create a positive charge is by removing electrons. We cannot say, oh, I just want to turn this positive and I want to turn this neutral. We have to move electrons to accomplish that. So we take this, we slide it over, and we essentially flip-flop the position of the carbocation by doing that. And the reason that this would happen is because we took our secondary carbocation and turned it into a tertiary. So there is a big energetic payoff by creating something that's much lower in energy. Now for the next one, this is an alkyl shift. And this happens when you have a secondary carbocation. I'm just going to shorthand this since my pen is being weird. Next to a quaternary carbon. So it doesn't have to be all methyl groups like the example that I drew here. It could be anything. But what makes this one specifically a methyl shift is that I have these 3 methyls here. And when I do this shift, I'm going to be moving an entire carbon group along with the electrons that bond that carbon to the quaternary carbon. So just like I did with the hydride shift, I'm simply going to take this and slide it over here. And that actually is going to have a pretty significant impact on the shape of my carbon skeleton. So I will no longer have a secondary carbon there at all. It's going to become tertiary. Oops. So this is the methyl group that I just moved there. And this carbon has become positive because I took electrons from it and gave them to the neighboring carbon. So sometimes students have a hard time understanding how this carbon skeleton changed. So let me apply a little numbering system here. If this is carbon 1, 2, 3, and 4, this is 1, 2, 3, and 4. If we want to number these methyl groups as maybe 5 and 6, carbon 5 is still attached to what is now the carbocation, but carbon 6 has wandered over to carbon 3. So that's how the carbon skeleton actually ends up changing, and we end up creating our tertiary carbocation on what was previously a quaternary carbon.